Hello and welcome. After a long break, I'm back with a good video related to Regressor. Today, we want to predict car prices. The dataset is from the Kaggle website. So let's get started. First, importing the necessary libraries. NumPy for numerical operations, Pandas for data manipulation, Matplotlib and Seaborn for data visualization. First step, reading and understanding the data. Here, the price is our target, and all the others are our X columns. So the changes we have in this case are feature engineering and encoding. Before making a regression model, we have to prepare the data. The data is real, so we need to check the features. For example, in line 3 and 4 in columns car name, you can see in line 3 it's written with space 100 and ls, and in line 4 it doesn't have a space between 100 and ls. So we may know they are the same type of car, but Python don't know that. If we don't know handle it, we don't fix this issue, something like this issues, Python will count it differently, so which can have a negative effect by creating duplicates. So splitting the company name from the car name column. To solve this issue, I took the column car name. We will have other challenges like using capital words. So we have to make them all the same. After we will go to do one-hot encoding, dummy variables, and this type of works. So here I want to use the keyword lambda. As you know, we have different kinds of keywords in Python, around 440 keywords that we used some of them in previous videos, and you can check my channel. So here I tell Python to use the method apply. So we can say apply per record for all of a column. Now I say come and consider an I, and wherever you see a space, split it. So now I put all of them into company name. Now all the company names split it and easily can select it. Now if I say company name to choose the first split names, by choosing 0, I can select the first split words. It gives me only the company names that I wanted. So I choose the first one and add the company names without their model. Now here I insert index 3, or let's say column 4, a feature called company name, and its variable is company name. Then I drop the column car name and in place true. It means it will be dropped in all next parts, and we will see only the name of companies without their models. Now I fix the names of companies, but if I use unique, we can see differences like Toyota or Nissan and so on. Converting all company names to lowercase to ensure consistency. So in the next how do I this say to Python? There are many ways. I used the following method. First, I told it to make all the words lowercase, and then I used the replace definition to replace the names. Now, as you can see, I don't have different types of the name like Mazda or other car names that I fixed. Next, outlier analysis. Another challenge that this dataset has is that the target is skewed. So for visualizing the data, if we look at the distribution plot of the price, let's look. We can see the price has a skewness to the right side. So we have outliers, and to reduce their effect, we can do logarithm, power transformation, and so on. There's no need to try all the ways. Boxcox can show you what to do. So logarithm is not always a good way, but we know taking the logarithm of a column decreases the effects of outliers and helps it become more normal. So in this case, I will model the price, and you can take its logarithm by yourself. Um, we have the method select the type. So here we tell Python to go to the data file and select the data whose type is categorical or numerical. So with include, we select the categorical data, and with exclude, we select the numericals. Here, numCal is the name of the column. So we can plot many EDA packages that I did before, and you can find on my channel. Here I use the pair plot from Seaborn. I take pair plot, and from cars I take the columns that are numerical and compare them two by two. For example, we have, as you can see, car ID, symboling, wheelbase, car length, and so on. From the scatter plot, I realized that my features like car length and car width can have correlation. So with the following code, we can look at their correlation, which we could also see in the scatter plot. So it shows that the correlation between car length and width are more than, as you can see in CarCoF, more than 80%. To conclude, we understand from different ways we can find redundant components. Remember, most EDA packages have correlation technicals, but a very important part is that most of the time they are not exactly correct because they consider linear definitions. That is not correct because some components are binary. So here the Pearson correlation doesn't work. And another issue is that the data can have missing values. Next, deriving new features. Here I added fuel economy from this formula that sometimes we may need to do it in our projects. to reduce columns or another reasons. But we normally need to remove the features that we combined. If here we remove city MPG and highway MPG and instead put only fuel economy, that would be sensible. But if we don't, it's not correct. But to be noted, I didn't remove to see their outputs. So here on cars, we do the method group by and count price means the count the means of prices for each name of companies or for each companies. They may have different types of cars. We want to find their mean prices. So then I make a copy so that I don't make changes to the original data. Then I told Python to do the merge data frame method. Now we reset the index and create a second price. So the original price becomes price X and the second becomes price Y. So price Y is merged according to company name. To prove, we can see the three list item are Alfa Romeo and its price is around 15,498 that we had before, as you can see here. So here in the next, what is cars range? We tell Python according to the price of cars, make a column and put its budget, medium, or height. So here cars range, which is our X column, is inspired by price. We have different methods. I use cut here. Now we will tell Python according to price y. Let's find whether the car's bin is lower, medium, or high. To be noted, the bins are the uh, numbers we choose from 0 to 40,000. Also, in cat, the third argument is labels, where I put cars bin. So it will put budget, medium, and hind in the column cars range. Now, in the next stage, I want to remove some columns that don't have much impact, like car ID and the others. So here we have these columns, and for example, you cannot see car ID and some other names. So I put selected features into cars LR to work on them. Next, dummy variables. So here I can quantify my columns. I can take the columns that are qualitative and encode them. Here is the code, but it has some points. Instead of using get dummies from pandas, I define the customized dummies function. Here, df dummies xdf. We give a column name and say from which data frame it originates, and put it into our personal definition that we call dummies. In the second line, the drop first is true, so it will become dummy, not 100. Then I said concat df and temp in the column shape. So temp contains the columns that become quantitative. So now I have some quantitative columns and the others also become quantitative. But then I drop the columns x that I give in place in true. And in the next parts, it will also be like this. Uh, The point is, here we did encoding before train and test, but it's better to do it after train and test. So in the next train and test and feature scaling. So here we trained 70% and we tested on 30%. So from cars LR, I got two objects, df train and df test. Next, I take numbers from the column above. This numbers is the numerical data. Now, for numbers, we will do three steps: train, test, split. So we did min-max scalar, and Python knows what the normalized numbers are. So now we rescale all the data between 0 and 1. So in the next, we had to do this for encoding as well. Encoding had to be done after train and test. Here we can see in price, for example, which columns have correlation higher than 80%. And we can bring them and do an update. I mean, we can remove some features which don't have high correlations. So first, I want to divide data for train and test by using a pop. Here I use the pop method. It removes and returns. So here it removes y train and we just have x train now. Now let's do build a model. We have a library called stats models. It's usable in high-level statistical models, so it gives advanced calculations in regression. So here I told it to modelize price from the column horsepower. So now it takes that and puts it into X-train, and in the next we have at constant. This is for calculating beta zero in regression. Then we come from stats models to take our regression model. The model OLS means ordinary least squares. So now we have to do regression on the train data. In OLS, Y train is our target. In in terrain, and the next one is our x. So now we fit it for the terrain model. So params in the property that works in regression variables. Only variables come from the uh, stats model library. We have the method summary. With this, we can see which time the model run. If the model dependent variable is price here, as you can see, how much r squared it has. So here coef const is our beta 0 and the horsepower is beta 1. In the next, I came to add another feature according to correlation. So now our price will be modeled with horsepower and curb weight. Now, as you can see, our R squared improved compared to previous one. Now here I added another feature, engine size. So R scored, as you can see, improved to 81%. But this way of adding each feature by hand to test is not logical when we have a high number of features. So we can use feature selection methods. We've achieved an R squared of 81% by manually picking the highly correlated variables. Now let's use RFE to select the independent variables which accurately predict the dependent variable price. To be noted, RFA is means regressive feature elimination. RFA is a backward search strategy. It means regressive feature elimination. So I called RFA linear regression and variance inflection factor. I bring linear regression from Scikit-learn and do the fit for it. Next, we tell RFE to select the features and the top 10 to select and then fit on X and Y train. In a list, it gives me three outputs in zip. First, the name of the X-train column name. Second, have true or false output to support the top 10 features or not. Third, gives their rank. The number one is the top 10. So we have a 10 number one. The number 11 is rank 2, number 12 is rank 3, and so on. Now, for the X-train columns, which have RFE support, I choose them. So now it selects the top 10 column names. For building a model, by using static models. Here I choose the top 10 from my X-train. Now with RFE, I find the 10 best features. Checking VIF or variance inflection factor. VIF gives a basic quantitative idea about how much the feature variables are correlated with each others. It's an extremely important parameter to test our linear model. If VIF is 1, it's very good. Here I create a data frame and put the selected columns. Then I append a column with the name VIF and tell it to select variance inflection factor, and then do a for loop for each feature. Then from VIF round its number to 2. Then sort the values. To be noted, before making sure about our features, we don't allow to use a VIF because it can cause us to remove or save good or bad features. So after p-value checking, we allow, or it's better to use VIF, to do VIF. So now we need to check if these 10 features are significant or not. We need to check the p-value. Here, the p-value of fuel economy is higher than 5%, as you can see. So we fail to reject and we have to remove it. And also the 12 is the same, and it has a it's higher than 5%. So here we drop 12 because of high value. Now we can drop also fuel economy. So dropping 12 and fuel economy, that if we want to check the R squared did not change. So the two remote features were redundant. Now calculating variance. So now we have 8 features that are important for us. Here, by checking VIF, dropping curve weight because of high VIF value, it shows that curve weight has high multicollinearity. Now we also drop this, and now we need to have a residual analysis of model. For final model, to build a final model, as you can see in OLS, we have a Y train price. It's our result. So we can see the training error, which we want to go toward the 0 side. To divide target and X, I use pop method to divide price from our X. Now we want to test, and we did these steps before for train. In our data, we don't have a const feature, so let's also drop it. Here, we do the same like before and drop the constant. So for making a prediction, here predict is validation. And here I took R2 score of Y test and Y pred. Now this R2 is for validation. We can see the result is the same as the state model. It's around 91%. So we can also use plots like this. We make two different indexes for the I in range 1 to 63 with step 1 to go forward. You can see the different lines together. The closer is the better. I mean, if these two lines to be close together, it shows the difference of actual and predicted results. So whatever the prediction to be near to actual is this is better. Another good plot is this. X is what was in reality, Y is what my regression model predicted. So we can check these two to see what number in predict and what number in the reality was and compare them. So this was a simple type of regressor. We have different types of regressors like support vector regressor, decision tree regressor, kind regressor, ensemble regressor, like GBM, and so on.